Ferdi Schüth, M. Pi Mulheim Ruhr, speaks about heterogeneous catalysis, a key topic in chemistry between basic research and commercial application.
Welcome back. The second session, Professor Ferdi Schüth from Max Planck Institute für Kohlenforschung, which I did not find a translation.
We don't translate.
You don't translate. That's what I got from the internet. We don't translate. Wilhelm an der Ruhr in Germany. I have briefly had a look at all the abstracts, of course, and it jumped on me. Haber-Bosch. So there's a procedure to produce ammonia from coal. Right? Both are on the wall in the Exner room. So both are Exner medalists as well. Both as well are Nobel laureates, but both have the Exner medal long ago. Now we will have contributions. Now we have contributions containing the buzzwords of our world, right? CO2, energy, heat transfer. What's the word? I always forget. It's not here. Sector coupling, that's what that was. We will have contributions from AIT Vienna, from Paris-Laudron University in Salzburg, and the TU Wien, which is just over the street. And without hesitation, I may ask you to the stage. The talk is titled Heterogeneous Catalysis, a key topic in chemistry between basic research and commercial application.
Many thanks. Many thanks for the kind introduction. I have to say, I feel extremely honored standing here, being a recipient of the Exner Medal, especially as I looked at the wall in the room next to this one. You already said Fritz Haber, Karl Bosch is on the wall. Karl Ziegler is also on the wall. He was my predecessor as director at the COFO in Mülheim. We don't translate because we don't do Kohlenforschung, so we try to not confuse people. This is the reason why you don't find the translation. What I'll try to do is give a somewhat broad overview, because heterogeneous catalysis is really in between fundamental scientific research and industrial application, and I had, well, foots in both domains, and the Exner Medal, I think, is exactly for this kind of research. Stuff which at one point has the chance to leave the lab. And this is what I will try to explain to you. I will use mostly parts from my own research, but as I said, I try to put it in a broader perspective. So heterogeneous catalysis is something which starts at the atom. This is aberration-corrected electron microscopy. So what you see, the bright spots are really columns of atoms. Then we have shapes of the catalyst, which you at one point fill in the reactor. A reactor may look like this. This is a multitubular reactor where you do reactions where a lot of heat is released. 20,000 individual tubes welded together, cooled by a cooling liquid, most often a salt. This guy standing here is Stefan Schunk. I'll come back to him later because he was instrumental in creating a company. That's what at BASF sometimes in the 1990s, but the reactors still look the same nowadays. This is industrial type reactors, and eventually you assemble them into a plant. So catalysis, heterogeneous catalysis, goes from atoms to plant size, so length scales of angstroms to 100 meters, roughly. Technically very challenging, high temperatures, high pressures. The Haber-Bosch process you refer to, something like 450 centigrades, 300 bars pressure, that's not easy to handle. Everywhere in the chemical industry, you have catalyzed reactions, plants where a catalyst is implemented. Essentially, probably something like, there are different estimates, 80 to 90% of all industrial production processes have a catalytic step in there. And mostly it's heterogeneous catalysis, which means the catalyst is a solid and what is being catalyzed is a liquid or a gas. There is also some molecular catalysis where you have molecules dissolved in something which do the catalysis. Industrially, the heterogeneous one with solids is the more important one. And again, you find many different estimates. Here I quoted one, roughly 4% of the global gross national products, the sum of the global gross national products are created by catalysis. The market size of catalysts alone is about 25 billion euros. The revenue generated with catalysts, which you fill in the reactors, is something between 100 and 1,000 times bigger. So 4% of the gross national product would be roughly 200 times. But as I said, this is difficult, but I think it tells you this is something which is not unimportant, catalysis. And very roughly, we can discriminate the types of catalysts. This is market size, this pie chart. Chemical catalysis for the chemicals we use every day or industry uses to make products. Refinery catalysis, this is mainly what supplies you with the gasoline or diesel fuel or kerosene you are using. Environmental cleanup of some of these production processes actually, or the catalyst coming out of the car, and the rest is polymers, petrochemicals. Petrochemicals mostly also go into polymers. This is why they are combined. So polyethylene, your polystyrene stuff you have in your kitchen, the packaging, this is all made by catalysis. So it is really an important field. Our world would look totally different without catalysis. I just take one simple example. This is the increase in the world population. This is the production of ammonia synthesized by the Haber-Bosch process, which we now have referred to quite often. And it's not by chance that these curves are running in parallel, because feeding the world is only possible by the fertilizers which you make from ammonia. There is not enough nitrogen fertilizers which you can just mine for. You have to synthetically produce it. The correlation continues. This was the graph I found. I added 2 new data points for 2022. So ammonia production on the order of 150 million tons per year, population at about 8 billion. So these curves just continue. So to feed the world, there is no way then to use ammonia fertilizers to produce enough food. And this goes back to catalysis. Just for the ammonia production, just for this production alone, we have 4 catalytic steps. From natural gas, by reforming, we produce hydrogen. Then we use the water gas shift to produce even more hydrogen. Methanation cleans up the hydrogen, takes out the traces of carbon oxides. And then you have the ammonia synthesis at 450 centigrades, roughly 300 bars pressure. Capacity, 170 million tons per year. Production volume, let's say 150 million tons. So without building new plants, we can make 20 million more tons, at least roughly. Now, there is another interesting catalytic process which was invented almost exactly 100 years ago in my institute, the Fischer-Tropsch process, very popular at that time, becoming again popular, and I show it for 2 reasons. First, because it becomes popular again, and I'll tell you why. Second, for ammonia synthesis, we roughly know why the catalyst is reasonably good and why it's working. Not exactly, but roughly. So this is the Christmas party in our institute, 1917. They look kind of serious. Well, it's at the end of the First World War. There was no reason to be very joyous. Institute was small at that time. Nowadays we are about 400 people, so this was 20-ish. And the Fischer-Tropsch reaction, and I have a small movie which the group of Rüdiger van Santen produced. So this is not my movie, but it shows you very nicely what happens on a catalyst. This is based on chemical evidence, but it's an artist's impression. This is not quantum chemical calculation. These green ones are ruthenium atoms. This is carbon monoxide, the gray and red. The white is hydrogen. And on this particle here, you form methane, nothing else. Useless for the Fischer-Tropsch reaction. Now, if the particle looks slightly different, if we have these strange kink and corner sites, so-called B5 sites, then you see suddenly there is a chain of hydrocarbons growing out, and not methane, but hydrocarbons are formed. And these hydrocarbons are wonderful diesel fuels. So the Fischer-Tropsch reaction produces diesel fuels, and interestingly, the Fischer-Tropsch reaction produces diesel fuels from CO, but you can easily get, if you have energy, CO from CO2. So if you have CO2 and hydrogen, you can produce synthetic fuels, and if you generate the hydrogen from renewable energy, you have renewable synthetic fuels. These are the so-called E-fuels. In Germany, I'm not sure whether that's the same in Austria, we have the word Flugscham. So you're a bit ashamed of yourself if you fly long distances because it's bad for the climate. If we would produce all the fuel by the Fischer-Tropsch reaction, well, I would argue times for Flugscham are over. So it'll take, let's say, 40 more years, still. So this is one of the few reactions where we know these B5 sites are very important. In most reactions, we don't really know what the active site is, which makes it very difficult to design a catalyst. And the system gets even more complicated. This is a picture from Mark Willinger's group at ETH. This shows you a platinum catalyst under reaction conditions during NO2 hydrogenation. And what you see is this catalyst, this is a platinum foil, is not at all static under reaction conditions. It's changing all the time. This is actually the work function, which is depicted here. It changes all the time. You have spirals forming, these boundaries are moving, the surface structure is changing. So even if you would know how a catalyst should look like to be good, it would be destroyed under reaction conditions, probably. And so this is the first topic I want to talk about. How do you find new catalysts if you don't, or often don't know what you're looking for? Well, you have to do many, many, many experiments. And there was one example in the late 1990s where people looked by high-throughput methods, which at that time were known from the pharmaceutical industry, and used it in material science. In this case, they were looking at phosphorescent materials. Phosphorescent materials, great example, because you produce a library, you shine UV light on it. If it lights up, it's a good phosphorescent material. So that's simple, still very impressive. It was something like 25,000 compounds by evaporation on this substrate, UV light on there, and then you find, well, different kind of phosphorus. Not very surprising. If you put europium in it, it's red. If you put terbium, thulium, other oxidation states of europium, it's green, so it's not really surprising, but this corner was interesting. So they were looking for white phosphorus. This was described in the beginning of 1997 at a meeting in Dechama. There was someone who gave a literature report, actually a conference report, look what people do in material science. This was a catalysis working group. We were sitting there listening, and I was sitting there asking myself, gee, this could work for catalysis. We had a heavy discussion in this meeting. Most people said, stupid, never works. Come on, high pressure, high temperature will never work. I dug out my notes, actually from this meeting. I hadn't looked at it for about 20 years. So this is from my notebook. I copied it last week, where I actually had the principle of high throughput sketched down. When I came back in the afternoon from this meeting, I went to the office where a few PhD students were and said, look, I think we should try this. This is how we should build a reactor. And then they build a reactor. The reactor, the very first one, looked like this. Very rudimentary piece of equipment. A brass thing, 16 parallel channels, common inflow, separate outflows. You would, in each of the channels, you would put your catalyst, and then we had a detection which you could switch between the different channels. So very basic, but that was the basis of the first patent which we filed. Later the reactors became a bit more sophisticated. This was already pressure capable and so on. And then at some point it was a PhD defense of another student. We were standing outside drinking lots of beer, which sometimes helps if you have such ideas. And I was standing with 4 people and said, you know, guys, when I ever had an idea which could be commercially interesting, it's this one of high-throughput experimentation. Why don't we do it? All 4 of them said, yes, let's do it. Next Sunday, we met at my home, and that was the start of the company. This is the principle. I go first to the company. It was HTE company. There's a logo on there. No, it's on the next one. So in 1999, the company was launched, incorporated. We offered this technology service, equipment, and research service to chemical companies. We had a first contract with BASF, which I knew extremely well at that time. I was very close to them. The second one soon with Chevron. And then it grew bigger and bigger. It immediately took off because I think we had really good technology. 2008, BASF acquired the first half of the company. They only kept the founders in because they wanted to incentivize them. So we had a contract that in 2013 they would buy our remaining shares depending on the development of the company, which was nice, which was good for us. So in 2013 they fully acquired the company. At that time we were at about 250 people. Now the company is at, I think it's down there, it's about 350 people. Revenues are on the order of middle 8 figures euros, so very substantial revenue. But what I think is, for me, the most impressive thing, I mean, this is not the guys running HTE, this is not me anymore. I'm out since 2013. But we were there 2 weeks ago where they updated us on the progress. HTE is now responsible for 10% of the central research of BASF, of a global, biggest chemical company. This tiny little thing which started with 7 people 25 years ago is now 10% of their central research. And that's, I think, quite impressive. Custom, and it makes a profit. Normally central research costs money. HTE actually makes a profit for BASF because they serve a global market. So basically whatever company you think about in the oil, chemical, catalysis industry, refinery industry, is customer of HTE. I would argue very clearly market leader. I show you some of the new technology developments in a second. I want to go back to this one here, which is my very favorite development. And at the same time, it's totally useless. But I like it, just scientifically. The problem is if you have these parallel reactors, you have to detect the product in the effluent of all your different channels, ideally in parallel at the same time, and not switch by a valve between the outlets of the different reactors. And here we have a method which really allowed you to do that. The idea is actually relatively simple. Here is your gas stream, and you have a laser. You pulse the laser, which is tuned to an absorption of your the product you want to detect. And if the laser hits one of these molecules, the molecule is excited, and so it gets hot there. If the laser is pulsed, it gets hot, you have a heat pulse, which translates into a pressure pulse, and then you put a microphone somewhere here, and the microphone will detect the pressure pulse. The intensity of the pressure pulse gives you the concentration. The time delay between the laser pulse and the detection in the microphone tells you where actually the laser pulse has excited such a pressure pulse. And this gives you a really basically truly parallel method. This is original readout data for 8 channels in a row. Here is the laser, here is the microphone. So the first pulse detected is very close to the microphone, the next pulse detected is the second one, and so on. And so you can truly in parallel analyze, and here is a comparison between gas chromatography, which is the standard tool for analysis, and this photoacoustic detection. I was totally proud. As I said, totally useless in industrial application. You don't want something specific which only works for one molecule. You want a generic method. And industrially, what is now being used is normal gas chromatography, mass spectrometry, infrared spectroscopy, which you can use for many different reactions. So we filed a patent, we used it in HTE, but never for a customer project. And so at the end, it was a nice publication. Still, I thought the idea is neat. So this is, I mean, just going back. So this was the first reactor here. This was the second. After 25 years, this is how the systems look like. This is typically 16 to 48 parallel reactors, 4 temperatures up to 1,200 centigrades, high pressures, everything automatized. There is a software environment in which everything runs. This is a bench scale system, not quite as highly parallelized, but for scale up in the chemical industry, very important. So typically you have 4, 8, 16 reactors. This is pretty big machines. So from here to here, we're talking something like 5, 6 meters. These are big units we're talking about. This is 4 to 8-fold, almost pilot plant scale, at least laboratory pilot plant. And this is the micro downflow unit, which is used by refiners. If a refinery changes their feedstock, so you run with Arabian oil and you change it to oil from, I don't know, Qatar or whatever, your catalyst needs to be adapted. And typically you need long trial runs to find the next best catalyst for this new feedstock. HTE by now has such good analytics for testing new feedstocks in the refineries that the refineries skip the pilot plant scale. They test their catalyst in these units at HTE, and then they go into production runs. And so that is a good business for HTE, just supplying the refinery business. So I would say this is now at least part of the standard suite of technologies to do catalysis research in industry, because we don't know everything about the active side, what we need to do. On the other hand, it's also the basis for artificial intelligence approaches. Because if you have lots of data which are obtained under very standardized conditions, and you don't know something for a rational development of catalysts, where you could use data-driven approaches and use AI. This is nowadays done. We did it actually about 20 years ago. I have a paper which is called Teaching Catalytic Intuition to a Computer. I think it's this paper here. First, we tried to analyze all the data, catalysis data from the literature, and we gave up soon because nothing was under the same condition, nothing was comparable. So then I had this student, Katharina Klanner, a very courageous woman, because she said, okay, I'll synthesize 600 catalysts and I measure 600 catalysts and get my own database. And since we had the high-throughput techniques, it was a doable task. It still was daunting, but doable. So she did it and classified catalysts for a very simple reaction, propene oxidation, into 4 different classes. Catalysts which burned everything, but not with very high activity. Catalysts which burned everything, but with high activity. Catalysts which produced acrolein, which is one target product you get from propene oxidation. And catalysts which essentially made hydrocarbons from different hydrocarbons from the C3 hydrocarbon. So these were the kind of different classes. We trained the algorithm and then looked at how good the algorithm predicted the performance of unknown catalysts in this reaction. The blue bars here is what you would statistically expect for each class, depending on the number of systems in the class. And the colored bars are the results of the algorithm. So the algorithm was 2 to 3 times typically better than a statistical approach, where I would say that's what roughly a medium talented PhD student in catalysis could do, which I thought was okay for just an algorithm 20 years ago. So nowadays this is becoming a hotter topic. People are really jumping on it. I stopped in about 2008 because I felt this is too much mathematics and artificial intelligence. I was too stupid for that and left that kind of thing again. But still, I think it's an interesting study. Having said this, it now sounds you don't know anything in catalysis what you have to do to get a good catalyst. And this is of course wrong. We have lots and lots of experiments, surface analysis where people really got insight into the catalytic reaction. So there is prediction. It's not all high throughput and data driven. We have understood a lot. And I would say the simplest guideline is you need high surface area. Catalysis happens on the surface, so you want high surface area. And this is just a thought experiment. Let's take a cubic centimeter of vanadium that weighs 6 grams and has a surface area of 6 square centimeters. So this is 1 square centimeter surface per gram. And now we take a saw with an infinitely thin saw blade, so we don't lose material. We cut this cube in 1,000 cubes, and then it's same mass, still 6 grams. But if you would add up the surface of the 1,000 cubes, we have already 10 square centimeters per gram. So each division by 1 order of magnitude gives you 1 order of magnitude in surface area. And so if you want really high surface area for a catalyst, you want to go, let's say, down to the nanometer range. If your division of material is nanometers, you have 1,000 square meters per gram surface area. And this is one key target in catalysis. Make particles small, then you have a lot of surface area, a lot of possibilities for reactions to run on the surface, and then first approximation, you will have a decent catalyst. So that was another element of my research at about the same time when I was working on the high throughput experimentation. This was the first discovery, not by us. This was a team by Mobil Oil Company. They produced a material they called MCM41. And this is what it looks like. It looks like a honeycomb. And the dark features here is SiO2, silica, sand or glass, but amorphous. And the size here of these white features, which is pores, is about 5 nanometers. So if you have a material which consists of an hexagonal arrangement of pores separated by about 1 nanometer sized silica walls. Well, 1 nanometer is what gives you 1,000 square meters per gram. And this is what the material has. That has approximately 1,000 square meters per gram. This was a totally exciting time in material science. So when I was working at that time, we said immediately, let's reproduce it. So we said, reproduced it, found it was reproducible. We could really synthesize the material, but then said, well, it's synthesized with surfactants. The surfactants form liquid crystals, and in the hydrophilic part of the liquid crystals, you can condense inorganic oxides, silica being the first example which the Mobil Oil people did. And then we said, if it works for silica, it should also work for other materials. And so we extended this. This was then this paper down here, which I did together with Georg Stucki. This was a different type of silica. This was tungsten oxide. This was again a different type of silica. So we extended the synthesis protocol, and you can nowadays basically produce anything you want with this kinds of surface area and porosities. One thing which a colleague in Korea did, Ryung Ryu, I found, when I saw that paper, I said, this cannot be true. This has to be a joke. What he did was he took the silica here, this silica, he coated a very thin carbon layer onto the walls of the silica, and then he leached out the silica, and then he had a replica in carbon. And these are now carbon tubes with a hole inside, and there is holes around these carbon tubes, which is the void where the silica previously was. You can even do SEM. This is something we did, where you can look into the top side of these particles. So you see these white features here, 1 nanometer thick carbon, packed hexagonally in this tubular arrangement, something like 1,500, 1,600 square meters per gram. And we recently, Dongwu, a great postdoc I had, who is now a professor in Guangzhou in China, extended this again to other compositions. Here, zirconia, we did iron oxide, which you can then use in catalysis. Generally, you do this by templating. And the templating is an extremely powerful concept if you want to produce interesting materials. These guys here, Pablo Arnal, Massimo Comato, Anyu Lu, said, one big problem in catalysis is sintering. If you use catalysts, you have them at high temperatures, particles become mobile. If they meet each other, they melt together. At the end, you lose surface area. You cannot keep the high surface area. And they said, what if we encapsulate the tiny little nanometer-sized particles in a cage which they cannot escape from? So what they did is they started with metal cluster, gold cluster. They grew silica around it. They put zirconia, which are thermally stable, on it. And then the silica was leached, and then you have a gold particle of a few nanometers encapsulated in a porous zirconia cage. This is what it looks like with the silica shell, so gold particle in the center of the shell. This is what it looks with the zirconia on there, with the rough on the outside, because the zirconia is now porous. And this is what it looks like when you leach the silica. Well, you have lost your stabilizing scaffold in the middle, so the particles end up somewhere on the inner wall. But they are all isolated, and so they don't sinter. This is just CO oxidation as a simple test. No aging, even after treatment at 800 centigrades. And Klein de Jong and Heiner Friedrich were kind enough to do tomography on this one. I think it's a great sequence of images. They did electron microscopy and then tilted the sample by 1 degree for every image, and then reconstructed the image. And then in the computer you can take out the gold, which they did in the first series. Now they took out the silica, where you can see, well, these gold particles are indeed completely separated even after treatment at 800 centigrades. And the next sequence is gold with the zirconia sphere still intact, where you can see it. So here is 1 gold in this sphere, there is 1 gold in this sphere, there is 1 gold in this sphere. So this concept works perfectly isolated. That was great, but gold in zirconia is a pretty useless catalyst. Doesn't do much. So I went to a very poor student, I would say, Carolina Galeano. It worked out nicely at the end because she was also a very smart student. And I told her, Carolina, we need something which is useful, and we need platinum in carbon. That's something you can use in a fuel cell with which to drive electrically if you don't want a battery car, hydrogen fuel cell powered car. So please make me platinum in carbon. She succeeded, but she couldn't get the loading, which is high enough. A fuel cell catalyst needs 10, 20, 30%, depending on the power requirement of platinum on the carbon. And with this concept, she never got to sufficiently high loadings. And then she said, well, why don't I just use the shell? The shell has pores, which are all identically sized, and then I fill the shell with platinum, and then each platinum particle is still encapsulated in these pores, which are all the same size. So she changed the topic, and that works. So this is platinum in carbon after treatment for 10 hours at 900 centigrades. If you do electrochemistry, use the catalyst before, do an electron microscopy analysis, look at the same region afterwards, you see basically the catalyst doesn't change. The only thing which changes, this is an overlay of secondary and transmission electron micrographs. The red ones are platinum particles. Here you have platinum still on the outside, which you can see because there are bright spots in green. That's the scanning part. If you do the transmission part, you see the platinum all over the place. After aging, the green bright particles are gone. These are the ones on the outside. We have lost them. But the red ones, which are inside the pores, are still there. And this is why these catalysts are really, really good and perform, I would say, almost perfectly. This is next generation catalyst. Cut a long story short, the benchmark here is platinum on Ketchen Black and platinum on Vulcan. These are the two industrial fuel cell catalysts which are used in the industry. And our catalyst outperforms Ketchen Black and Vulcan at low current densities and at very high load at high current densities in true fuel cell experiments, not just in some sample experiments. And our fuel cell colleagues, Hubert Gasteiger, Karl Meyerhofer, I'm not an electrochemist, they were impressed because they said, well, we have 3 million papers on rotating disk electrode measurements where catalysts are supposedly better, and they all fail in single cell fuel cell experiments. Here is finally one which really survives. Coming to a last part, just briefly, which makes me tick nowadays, mechanochemistry. All I showed you before, you run the catalytic reaction by heating up your system, heating up the reactor. You can also introduce the energy by mechanical forces. And this is one example where we do that by mechanical forces. Alpha alumina, which you know from grinding paper, also as a gemstone, corundum. Sapphire is a titanium-containing corundum, gives you the nice color. Very hard material, almost impossible to get with high surface area, because the way to make it is calcining it to about 12 to 1400 centigrades. And at 12 to 1400 centigrades, everything sinters and you get big particles. So you lose everything. There is a way to make high surface area alpha alumina. You go via a somewhat exotic aluminum oxide hydroxide. The problem is in this line. 450 centigrades, 1200 bars pressure, hydrothermal for more than a month. So this is not really viable. And then Amol Anrute took boehmite, put it in a ball mill, milled for 3 hours, and got alpha alumina. So that's Amol Anrute who had the task doing that. Here is the diffraction patterns. After 3 hours, you essentially only have alpha alumina left. If you do electron microscopy, you see you have small 10 nanometer sized particles, 130 square meters per gram. There is, when we published that, there were 5 to 10 companies who contacted us and said, can we have this material? The problem is we need to scale up. This is always tricky in chemistry. We now have reached the roughly 100 gram scale in this so-called Simoloyer mill. This is not the mills you know from your laboratory. You have a big 2-liter vessel in our case. You can buy them up to 900 liters, but then they cost $1 billion, so I haven't done that. So I have the 2-liter scale, which is still expensive. And you have these rotating blades. You fill it with balls and the powder, and then you let it rotate. You hit the powder, and then you get alpha alumina. Here, even after 2 hours, with relatively little impurity, and the impurity we have is innocent because it's zirconia. So this is the basis, this and some other developments is the basis for a startup company which Özgül Akbaba is currently setting up. She has just won 1.3 million euros for the next 2 years to set up or to build the foundations of the company. Then she will license the process from the Institute for the alpha alumina and for some carbides and other things. And hopefully it will be a successful company producing material. Coming back to the beginning and the guys in the next room, Haber and Bosch. 450 centigrades, 300 bars pressure. If you put nitrogen, hydrogen flowing through a ball mill and you shake with a catalyst, you produce ammonia at room temperature and atmospheric pressure. This is the outlet of this reactor. This is a wet indicator paper. So turning blue means there is something alkaline, which is ammonia. Of course, we did a more careful analysis here with a real infrared detection. So for something like 70 hours, you produce ammonia to 0.25%. This is shut down. The sparks here are shut down overnight. And these are two fully independent runs with fresh catalysts, so it's completely reproducible, this reaction. This was still at somewhat elevated pressure, 20 bars. This is room temperature and atmospheric pressure, where you can still get 0.1% of ammonia over this catalyst. And you can even avoid the deactivation. We have cesium as a promoter for the catalyst. The cesium reacts with residual oxygen from cesium hydroxide. If we add more cesium to sacrifice some of it, it retains the activity over 90 hours, so roughly a week of experiments. That actually made it into Frankfurter Allgemeine, which for catalysis research is difficult to get in. I'm not claiming we will replace the ammonia plants by these little mills running all over the place and producing ammonia, but if we can get these kinds of activities at room temperature and atmospheric pressure, there needs to be something done by the milling which could provide a template to produce more active and better catalysts, which would do it also in the plant. And this is what comes next. I just got an ERC grant where we look into what really is underlying these phenomena which we have in mechanochemistry. It's essentially unknown why the reactivity is high, and this is why it's fascinating to me. I want to understand. I have about, 4 years left until retirement. In these 4 years, I want to understand what's going on in a ball mill and why systems behave so differently than when we just heat it up. So I have taken you through a journey in catalysis from atoms to reactors, but also from fundamental research to real-world applications and companies providing services. I'm only the one who presents what many other people have done. I never counted how many people. I just collected a number of previous slides of the group. I see Ferdi and Christian here, who are probably somewhere on one of these pictures, but there are many other people who are involved, hundreds of people overall. I didn't find a high-resolution picture. This is the initial team of HTE, actually with 2 accountants here. I would discount them. Still, they helped us financial planning. So Stefan Schunk, that's me. That's Wolfram Stichert, who is now CEO. This is Dirk Diemut, who was CEO for the first 12 years. Wolfgang Strehloy, John Newsom, and Armin Brenner. Half of them are still with HTE and producing the great stuff they are doing. The others have gone to new endeavors. All of them I really thank deeply, because I alone couldn't have done any of this. I thank you for your attention, and I thank the foundation for awarding me the medal. Thank you.